Next, you will be hearing a presentation from Professor Chao. Professor Chao received his PhD degree from Michigan State University, the United States of America. He is currently a distinguished professor at the Electrical Engineering Department of National Yangming Jiaotong University. His research interests focus on sensors, actuators, and their readout circuitry. Today, he's going to give us a presentation entitled A Flexible PPG Sensor Patch for Vital Biosign Detection. Ladies and gentlemen, let's welcome Professor Chao.
Hi, hello everyone. My name is Paul Chao, a distinguished professor at NCTU, National Jiaotong University, Taiwan. It's my great pleasure to present to you the recent work have done by laboratory, which is on a new flexible PPG sensor patch for a number of different biosign detection. This talk is specific made for the 2021 summer school for IEEE Sensor Council. Here's the outline of my talk today. First, I will talking about the basic principle of a PPG sensor, then introduce to you about the design and the fabrication of a sensor patch for the PPG signal, then followed by heart rate variability calculation, particularly for AFib detection. Then the next one will be using the PPG waveform to calculate blood pressure. Finally, remote PPG for heart rate, not only the software algorithm, but also the hardware FPGA implementation. The first part, operation principle of a PPG sensor. There are many commercial PPG products available in the market. For example, there are some health bracelets with LED and PD for measuring heartbeat and blood oxygen. And some other, very few of them, has both sensors, ECG and PPG, for blood pressure. And we are developing the PPG only, okay, for measuring blood pressure, blood flow volume, and in the future, it's not successful yet, blood glucose. Here are the two PPG devices we have developed successfully. The first one is handheld device in the picture over here. The second one is a patch. By using either the handheld device or patch, we can obtain the PPG waveform of a blood vessel of a subject, then transmitting wirelessly the PPG waveform to the laptop or desktop and eventually to the cloud. Then using the waveform, the PPG waveform we have obtained by the PPG devices, we can try to estimate the blood pressure or blood flow volumes. Here's the basic principle of the PPG. Essentially, we have two different very important components, LED and the PD. So we can place the LED and PD on one side of the human body, or which is called reflectance type of a PPD module, or you can try to measure the PPG signal on a finger where you have one LED on one side and the PD on the other side. So basically, PPG is a non-invasive measuring methodology. It's optical sensors. It's using the optical power at fixed wavelengths emitted by LED and eventually going through the blood vessel to reach the photodiodes. So the PPG module, especially in this study, we consider is a reflectance type. So for this type of a PPG, we have the PPG LED and the PD on the same side in a module to be attached to the subject's skin. So the lighting power coming out of the LED will eventually reach the PD along a banana shape. So this kind of phenomena is called Beer-Lambert load. So the signal received by the photodiode supposedly with the banana shape, the optical path going through one of the blood vessels. So the pulsation of blood vessels supposedly to be embedded in the signal obtained by the photodiode. Here's a typical PPG, low PPG signal, where we can see there are two different components, AC and DC, constituting the entire PPG signal. AC is small, often less than the 5%, or even smaller as compared to DC, a much larger components, usually more than 90% of the PPG signal. However, the pulsation of the blood vessel corresponding to only the AC components. So therefore, there must be a very well designed readout circuits in analog and digital to be able to extract the AC signal from a real PPG waveform. Must be noted that only a high SN ratio of PPG signal will give a chance for accurate estimation of the blood pressure and the blood flow. On the other hand, the readouts needs to be also designed in a special way that the readouts will be able to remove the motion artifact in order to increase the chance of acquiring high quality PPG waveform in the real world. The readout circuitry, including the analog part and the digital part and the post-processing unit. So the readout circuitry for the PPG over here should be able to take care of the interference from the ambient lighting and motion artifact. So the approach we have adopted is trying to use a very good high order low and high pass filters to mitigate the drifting DC components. So there are even some of feedbacks from the digital register map to do some decision back to the analog part to achieve the goal that we can get rid of DC drifting, which is a very low frequency component, and also get rid of high frequency noise. Here's the readout PCB board inside the handheld device. So essentially there are two different wavelengths PD, the green light and the red light. So this handheld device can be used to predict blood pressure, blood flow. It's wireless USB connection, and LED PD can be changed to different wavelengths LED. And inside the PCB board, there is also ACG auto gain control and auto light intensity control in order to take care of different skin color and different subjects variation. Here is the LED and PD module inside the PPG handheld device. Here we have 4 different wavelengths and also associated PD along the 4 different wavelengths LED. The distance between the LED and the PD is actually optimized based on very detailed optical simulation. Here, I'd like to show you the details of optical simulation to figure out what's the optical optimal distance between the LED and the PD inside the LED part, LED and PD module. Here is the figure that we're using the optical simulation software to assume the LED PD module and wrist artery and all the other tissue and skin. Now here's the top view, all different parameters of the LED and PD module. Here's the optical simulation result. Here we can see the different wavelengths will give you the different penetration depths of most of the optical power. So where you can see the longer wavelengths will give you the deeper penetration of most of the optical power from the LED PD module to the blood vessels. By doing a lot of simulation, and finally we can figure out that for the wavelengths of 530 at 660, the optimal distance between the LED and the PD is about 2.3. And as for the other two longer wavelengths, LED and PD, so the optimal distance between the LED and the PD is about 2.85 millimeter. So based on simulation results, we finalize the design and the manufacture eventually at the end, the LED and the PD module shown over here. Having designed successfully the new PPG module, we go ahead to take the measurement by using the new PPG module we have designed, and also doing a comparison with the other commercially available PPG module. One's A brand, the other one's T brand, and the last one is the PPG waveform obtained by our LED and PD module. As you can see that the aspect ratio of our PPG module is a little bit better than the other two commercial PPG module. As for another very important aspect of the performance, the AC-DC ratio, our new PPG module actually can give you a much larger AC-DC ratio than the other two commercial brand PPG module. After the PPG module, we need to design the analog and the digital circuits to derive high quality PPG signal for the accurate estimation of blood pressure and blood flow. One of the very important design is the analog filter. So here is the very basic analog filter. Essentially, we use the bandpass filter. Most of the filter will have a low pass cutoff frequency at 0.7 and a high pass of 2.4. Essentially, try to get the PPG waveform around the heartbeat. There is also the digital unit for the signal processing. Essentially, they are before we try to calculate the blood pressure and the blood flow, we need to check if there is a saturation outlier, and also need to check the power spectral density is in the normal fashion before we really to calculate blood pressure and blood flow. Once we have quality PPG signal, then we can use this PPG signal to calculate the blood pressure. It's either in a laptop or in a cell phone. And this calculation algorithm actually need to be calibrated with gold standard data. For example, over here, using an Omron to have gold standard data of blood pressure. Here's the app we have developed successfully. Once the subject using a handheld device to have the PPG waveform, you can transmit it to the cell phone and finally to the cloud for calculated blood pressure. Part 2, PPG sensor patch. Hi, I'd like to talk about the motivation for us to develop the PPG sensor patch. The PPG waveform also obtained by the commercial PPG bracelet. But however, if you look at the waveform, it's often contaminated very seriously by the environmental lighting and the motion artifact. The subjects under the measurement must be kept stationary for the quality PPG waveform. Otherwise, it's very difficult to have an accurate measurement of the blood pressure. On the other hand, for some other chronic vascular patients, they are often asked by the doctor to wear such kind of equipment, ABPM, ambulatory blood pressure monitor all the time, in order to have a continuously long time measurement of blood pressure. But in this way, the patient need to wear this kind of equipment all the time on their body, which is very heavy, cumbersome, inconvenient for them to wear it for a long time. Therefore, if we can develop the PPG sensor patch, which can overcome the motion artifact, which is the main drawback by the commercial PPG bracelet, and also very small and lightweight, can also provide long-time continuous data of blood pressure as opposed to a cumbersome, inconvenient ABPM. In such a way, our patch will have its value in the market. And the PPG sensor patch is actually fabricated by the organic material for the OLED and the OPD. There are several important layers in the OLED and the OPD, which are all in the nano thickness by special design process of deposition. And for the first version of OLED patch, we use two different wavelengths, green and red, for the OLED. And the layout of OLED and OPD are actually optimized to overcome the mispositioning and the motion artifact. So therefore, we should be able to have high quality PPG signal out of this OLED, OPD PPG patch. So hopefully we could have very little motion artifact effects, very robust to the mispositioning, and very good feature, clear feature for estimating blood pressure and blood flow later on. Here's the very new self-adaptive readout for the PPG patch. Essentially, there are many different algorithms in the digital units to help to feedback to tune the different parts of the analog circuits. For example, there is a tuning on the cutoff frequency dynamically for the filter, and also dynamic tuning on the gain set up by the PGA. So it can, as compared to the previous version of the readouts, it's more capable to remove the ambient lighting interference and the motion artifacts. And of course, you will have much more stable DC and a lower noise by the low and high pass filter. The previously mentioned highly adapted analog front end and the digital units has several specially designed circuit block shown over here. One is a wide dynamic range TIA, another one is a fourth order GMC low pass filter, and the PGA and also PWM DAC in order to have the determination by the digital units back to the analog part to tune the TIA and GNC low pass filter, especially the cutoff frequency, in order to be adapted to different skin color, different optical property of tissue, bone, and muscle from different subjects. We have successfully taped out the highly adapted analog front end and also the digital FPGA chip to finally realize the highly adapted tune from the digital to the analog chip in order to have flexibility offered by the chip for different subjects in terms of different skin color, optical property of tissue, bone, and the muscle. The next part 3, heart rate variability, HRV. Once we have the PPG patch ready for measuring quality PPG signal, we can use this PPG signal to calculate HRV. HRV are originally defined based on the ECG signal, which are the indexes calculated based on IBI interbit intervals. So by looking at this IBI, we can evaluate the neural inferences on the cardio-regulatory function. Recently, there are many efforts have been done. One of the efforts is by Apple that people start to use the PPG instead of ECG to be considered to compute the HRV. So therefore, our effort over here is to use the PPG sensor patch to measure acquire quality PPG signal for calculating HRV. Here's a complete list of HRV indexes. So these indexes can be categorized to 3 different groups. The first one is in a time domain. The second one is in a frequency domain. And the third one needs to be calculated by the Poincaré plot. Among these indexes, it has been proved by many studies that the RMSSD and the PNN50 are 2 of the indexes highly correlated to atrial fibrillation. Once we have a quality PPG signal, we can develop effective AI algorithm like over here, the CNN, to process the original incoming PPG signal to distinguish it among the NSR, atrial fibrillation, and the other arrhythmia. Here's the traditional methods where we use handcrafted feature based on RNSSD, PNN50, and the other feature of IBI. The recent effort by our laboratory, we try to convert the PPG signal first to the Poincaré matrix, then using the CNN classifier, try to tell whether or not this case is NSR, atrial fibrillation, or the other arrhythmia. So once we have the PPG data, we try to process the data into the Poincaré plot first, where we have the RR interval in the vertical axis and the previous RR interval in the horizontal axis, and then turning into this plot into a matrix. Using this matrix, all the data can be provided as the input to the CNN based on the effective training on the data in a time window of 20 milliseconds. And finally, we can achieve the accuracy of 97.8%, a sensitivity of 98%, and a specificity of 97%. The result over here shown is pretty good, superior actually to all the reported prior arts ever published in a paper. Part 4, blood pressure prediction based on the PPG signal and the AI model we're going to establish. Here's the schematic of a cardiovascular system of a human being, where you can see at the right hand side is the artery system, while at the left hand side is the vein system. The pulsation waveform will have a different characteristic at different locations of a cardiovascular system. We are particularly interested at the PPG waveform at this artery, which is shown over here. This is actually a superposition of forward and reflected waves. In result, there are two different peaks. The first one will corresponding to the pulse wave from the heart, while the second one is caused by the reflected pulse wave from peripheral limbs. Therefore, the interval between the two different peaks will be somehow inversely proportional to the pulse wave velocity, which using this information, we can in some way try to calculate predict the blood pressure. And taking this into the consideration, we actually later on analysis, we are trying to segmentize a single PPG cycle to multiple time interval for the AI analysis later on in order to have accurate blood pressure prediction. Based on the theory and the principle we have been talking about in the previous slide, where we recognize that the time interval in a typical PPG signal is highly related to the blood pressure. So that convinces us that we should go ahead to establish a deep learning CNN model with the input as PPG, velocity of PPG, and acceleration of PPG to this model, and using different layers finally to be a flattened layer, and the final inputs of all the personal information to this unit to be combined with all the PPG information in the final layer, that giving us the chance to have very good estimation for the SBP and the DBP based on very effective training involved. The same work has been done as what we did for the handheld device, that the patch also connected to wirelessly to an APP. Okay, the APP can show the PPG waveform, and eventually also over here to give you the final estimation of a blood flow or the blood pressure, the SBP and the DBP, and also the heart rate. Having successfully established the neural network model and the deep learning algorithm, okay, we will be able to estimate the blood pressure and the blood flow in a required accuracy. It's actually shown over here. It's a video. There is a patch, and there is a PPG waveform. And once it's collecting about 10 seconds of data, then finally can show SBP and the DBP. On the other hand, we also are using the readout with the capability to remove the motion artifact. Later on, it's shown over here in this video. You can see the capability to reject the motion artifact. You can see over here later on, the arm over here will be moving up and down, and the PPG waveform still can maintain its basic characteristic over here. Then once we have a quality PPG waveform, even though there is a motion artifact, then the deep learning convolutional neural network could be used with the better extraction of a feature and the better estimation of a SBP and a DBP. Here are the estimation results of blood pressure. We can see from these two figures. The first one is for the accuracy of a SBP. The second one is for the DBP. That the error associated with the SBP and the DBP estimation are 0.46 plus or minus 7.56 millimeter mercury, and the other 0.14 plus minus 4.87 millimeter mercury for SBP and DBP respectively. And this mean error and the standard deviation is actually quite within the standard setup as we have seen for those figures. In those figures, that's the standards of the AMI, American standard, and also the British Health Service standard. Part 5, remote PPG for estimating heart rate. This is another effort by our laboratory to estimate the heart rate from a video. So the total work is some kind of a remote estimation on the heart rate. So first, we will have a detailed image from a subject, and using the region of interest, try to isolate the subject face from all the other background information, and then using the averaging to get rid of the noise. And the next one is a critical step. We try to develop an algorithm of independent component analysis, try to figure out what's the primary direction showing us that all the information about heart rate, then convert the signal after the ICA to the frequency domain, and hopefully we can have the highest peak that's corresponding to the frequency of the heart rate. So once we have 3 different incoming signal from RGB based on many digital image, okay, we will perform the independent component analysis over here, and trying to try out many different combination of incoming 3 different signals, and using some kind of iteration at the maximization of a non-Gaussian value, and hopefully this iteration will give us a result with at least one signal over here is at a frequency very close to the heart rate. All the previous computation algorithms were implemented by an FPGA system, a digital circuits. The block diagram architecture of the digital circuits is shown over here. Essentially, there are input data from an image sensor, and then processing the data, convert it to the RGB, try to detect where is the skin, try to figure out what's the region of interest, and then execute the heart rate algorithm based on the ICA, and finally output to have the heart rate. The entire digital algorithm shown in the previous slide are controlled by a design finite machine. So there are several different steps, and the correlation of the different steps are shown in the figure over here as the finite state machine. To implement the entire digital algorithm in an FPGA, it's a little bit complicated. The detailed architecture of the heart rate algorithm by the FPGA is actually shown over here. There's a control unit constructed and realized by the finite state machine as stated in the previous slide. And they are pre-processing, and then there are pipeline architecture to realize the ICA, independent component analysis. And then once we have the result of ICA, then we will convert all the information into the frequency domain. Then we could have the very good estimation on the heart rate, and finally output the heart rate. Here is the result we have based on the FPGA unit implementing the heart rate algorithm. Essentially, a better result are shown using a sampling window of 60 seconds. Here are the plots showing that the correlation between the estimation of heart rate by FPGA based on the ICA as compared to another oscillator data which is regarded as a gold standard data. So you can see all the data pretty much concentrated on this dashed line, which means that the estimation give you a very good accuracy. Actually, the error is represented over here by the mean difference, the standard deviation, as 0.67 plus minus 5.09 BPN, which is very good. Here's a video showing you that how the entire hardware system is implemented. Over here is the estimator showing you the gold standard data of the heart rate. Another one is a PPG board. Inside this board, the entire algorithm is implemented in this chip. So the entire system is able to show the heart rate over here in a real time. So you can see the number over here is about 71. It's very close to the 72 over here, showing that the very accurate estimation of heart rate by our FPGA system. Here's the performance comparison table of the technology we have developed for the remote PPG as compared to all the other prior arts. So here's the first one and second one are the result by using our methods and technology based on the 60-second and 8-second of the data. And all the others over here are reported by the other papers. So among these all the other studies, there's only two actually implemented the algorithm of the heart rate into the Verilog in a FPGA hardware. So particularly compared to the result, the accuracy of heart rate by these two different studies, that our accuracy over here plus and minus 5.09 is particularly lower than the 7.07 and 7.8 by these two different studies. So therefore, showing that the much better performance presented by our study. I'd like to conclude my talk today based on a basic interpretation of a PPG sensor as correlated to a human cardiovascular system, that the time intervals involved in a typical PPG waveform is actually highly correlated to many different biosigns like AFib, blood pressure, and heart rate. So using that kind of assumption that we can establish a CNN model to predict whether or not a subject having AFib based on the point cloud rate and the CNN, and the resulted accuracy can be achieved as 97%, I should say 98%, which is very accurate. And also we can use the PPG waveform to predict the blood pressure, SBP, and the BBP. And using our CNN, we can achieve the 2.0 plus minus 6 millimeter of mercury and 1.87 plus and minus 4 millimeter mercury, which is relatively accurate as compared to all the other studies. So the arrows presented over here can give us the chance to pass the criteria of for the FDA approval based on the standard of AMI and the British Hypertension Society in grade A. And in the final chapter of our talk, we actually also implement successfully a function of a remote PPG by an FPGA system. So an accuracy of 0.776 plus minus 5.09 BPN as compared to all the previous prior arts, which is the best result. So actually all this estimation is accomplished in a period of data in 6 seconds. So that's all about my presentation. Thanks for your attention, and you are welcome very much to ask questions now.